key, people try to unlock the mystery of the universe. This talk will not take you to the universe, but this talk will take you to the journey of one particular key to unlock the mystery of the universe. One particular key which once rejected only because philosophical reason, but also this particular key, this particular number, nowadays play crucial roles in today's science and technology. Please welcome Professor Markus Wono Budhi from Institut Teknologi Bandung with talk titled The Number I, from I Am Possible to I Imaginary Through Intelligent Mind. Please welcome.
Good day. Today I just like to talk about what say I was wrong when I'm teaching complex variable. By that time, I said to my students, some of them are in here, that the quadratic equation should have a root. But very fortunate that by that time, nobody asked why we should have a quadratic equation to have a root. Right now, I like to see, after I read some history books, that the mathematics is not something like that. That is beneficial to have something square root of negative. First, in this talk, I will go together to see the history of this number. Okay, long time ago, before iPad, iPhone, mathematics has number I. Yeah, usually we just introduce that the number I is the square root of -1, and we said that this is no real numbers, but we will use it because there is a lot of application. I think by that time the student and also many people say that the mathematics is forcing something that is impossible to be possible. Yeah, so I like to see from the beginning, from Egyptian era until, but for the usually subject in complex, I will not include it, but it's only, I found it's in the other books. So I hope there are a lot of teachers in here, so to see how the mathematics is discovered, and like Wim before. So in 1993, the Russian Egyptologists bought a mathematical papyrus, so it's just like a book. But only in 1930 that can be translated into can be understood by people in other languages from Russia. In that papyrus, in the book, I said easily, that the Egyptian can compute the truncated square pyramid. The object something like this, I think. But by that time, there is no algebra yet, so just computing the numbers. So, in order to find the volume of this one, we can just measure the base and also the length of the skew edge. On the papyrus, on the books, show that the Egyptians, they said, knew about this formula. So the APC is the, say, if this is square, then we just need to have A square, AP, and B square. So if this is another parallelogram, then it's just the area of the bottom plus the area of the top and multiply by adding square root of the multiplication of this one. And also that is it's strongly knew that the Egyptians know how to calculate h if APC is known. There is a well-known US historians that they claim appearing the square root of the numbers found in the first time in these books of Stereometria of Heron of Alexandria. First, he said that in success to it means that we can verify that if A equal 10, B equal 2, C equal 9, we'll have a right volume. But for the second example, if A equals something like this, then the h will be negative. Even Heron, the famous people, if we did plane geometry, he just wrote square root of 63 comparing instead of minus 63. So I like to show that even very famous people can do something wrong, but the most important thing is the next step after they did something not so right. Okay, there are many problems actually to see that they face with the problem of square root of negative numbers. Like Diopantus proposed some problem, something, what is the area, is there any right triangle, the area is 7 and the perimeter is 12. Of course, if you use a variable, then we will find something equation, something like this. By that time, Diopantus knew that the equation has no root. And the 600 years, about 850 after years, the Hindu mathematician said that the negative of the square root of the negative is impossible. Yeah. Okay, but now we see solving the third degree polynomial from Cardano, the Italian mathematician. Could solve the third degree equation in special form. If you have a third degree polynomial, something like this, using the linear translation, then the terms x squared will be disappear. The way to solve this equation by Cardano is reducing to the second degree, but by adding new variable. That is, usually we have x equal u plus v, so two variable, substituting as putting into equation, then we will have equation something like this. Then if we put u cube plus v cube equal q, and because this is the same, then 3uv equal p. If we power it to thirds, then we will have two numbers. We know the sum and we know the multiplication. And then we know that the u cube and v cube is a solution of quadratic equation. Then the quadratics will be y squared qy plus p over the 3 cube. Now, the solution will be something like this, and then the original problems will have something like this. If you have, of course, can be switched between u and v. So, suppose we have something like this, x cubed plus 3x minus 4 equals 0, then the solution will be something like that. If you know that difficult mathematics in high school, there is a problem to show that this is actually 1. So this is the example that we can work with something outside of the integers, but we will have an integers. How to show that this is to be 1? Because the original equation can be factorized something like this. Because there is no root, and this is the only one of the real roots, then this must be equal 1. So the next example is the solution polynomial is something like this: x cubed minus 15x minus 4 equals 0. Then the solution now will be square root minus 1 in here. Then because this one has many solutions, then this number should be one of this one. Yeah. But because the form, then everybody suggests that this must be equal 4. This is, I think, in 16th century. Yeah. So the Cardano actually knows that the square root of negative number has no meaning at that time, but he tried to keeping working with that numbers. So one of example is problem something like this by Cardano, that is divide 10 into 2 parts and the product is 40. Then they will have, if we have something general formula something like this, then the solution will be a square root of negative number. But then Bombelli explaining what happened in that one. So Bombelli said that the square root of minus 1 multiplied by square root of minus 1 should be minus 1. For us now is not strange because we know the complex numbers. But by that time, this is, Bombelli said, this is just wild thoughts. Yeah. So, to show that this one is equal 4, then by Bombelli, if we power it 3, this form will be exactly 2 plus 11 square root of minus 1. So, by substituting similar form, then we will have x equal 4. So this is the example again that works on the real numbers, but then we use the complex numbers. Yeah. Besides the successful of Bernoulli, then many people said that the square root of negative numbers is still impossible. Even for today, we call it I is not intelligence, but it's imaginary number. So, to make it real, many mathematicians to give some geometric interpretation. For example, Caspar Wessel, I think, in the proceeding of Copenhagen Academy, and also Arkan, I think, yes. What he tried to give an interpretation of the that number is first, if we have equation something like this, and for example p greater than c, so the root are real, then they give illustration, so this is minus p, assume p and c is positive, then the c is something like this, and we make a circle with radius p, then we will have the root in here and in here. But now, if p less than c, then the root is not real. By that time, they try to draw the complex numbers is something like this. If p, c, then this is the square root of p square minus c square. Yes. That is a weakness in here, because if p to be smaller, then the I and minus I will be together in here. But now, in the modern vector drawing, then the minus p will be in here, and the c in here, and then this one will be the root. So if the p go to here, then it will be in here, and this one will be in here. Then there is two representation of I and minus I. So although it is simple, but by the time they have no solution yet. So we are jumping to 19th century, that the Arkan consider the complex number is a plus pi, and he drew in the René Descartes plane. So like we usually this is the real and this is the imaginary. Also by that time, the Hamilton in 1930 defined the complex number as a pairing. So this is just considering like we wrote the rational numbers, a new numbers, by the old number, that is p and q are integers. So the addition operation is something like this. The multiplication operation is something like this, because if we multiply, this one will be a1 multiplied a2, p1 and p2 will be minus. So this is there is minus here, and the multiplication rule is something like very coming from the sky. So this is happened because by Cardano formula, that one. Now, do we need a complex number system? If we have a series something like this, then I think in the formal way, if I multiply by 1 minus x squared and then multiply, then this will be gone to be 1. So, if I have something like this, then as an informal way, this series will be something like this. Yeah, I can do something computation, but right now I just drew the graphics. So if I drew the two terms, I will have something like this. 3 terms will be something like this. 4 terms will be something like this. So there is no in this part. So it means if we know the series, then we know that the series will have meanings at the absolute value x less than 1. But now, if we have the series something like this, then the sum will be something similar before, then the series will be something like this. Oh yeah, I forgot. Before we can understand it, if we start from 0, then we cannot jump to x equal 2 because there is some singularity in x equal 1. Yes? But now, for this one, there is no singularity in R. So we expect that the series of this one will convert, will be the same on this term for the whole real numbers. But it's not. So, if I took just 2 numbers, 2 terms, if I took 3, 4, then you can see that the sum will be only has a meaning in -1 to 1. Yeah? If I put it some more again, and then if we put some more, then it will see that we just has the area in -1 to 1. That is what happened. So in the first series, we can understand that if we start from here, we cannot jump to here because there is x equal 1 and of course x minus 1. Also, it is a jump in here, there is a division by 0. For division by 0, from the beginning until the next one, keeping always, there is no division by 0. But now, if this one, there is no singularity in R. But if we consider it in the complex plane, then we can understand that this series cannot jump from here to here because we should consider on the circle with diameter 1. Yeah. So we show that, so this is the Jacques Hardamat say that the shortest path between 2 facts in real domain pass through the complex domain. So there are a lot, something we can understand it on the real variable using complex variable. So if you have a difficulty to accept that the problems the complex numbers is just pairing or something like that, then actually we can see that the complex numbers can be inside, that is inside the collection of matrix. So if we consider this one, so it is like as before, just consider these complex numbers, writing the new numbers using the old one, that is the real numbers. So the addition is something like this, and the multiplication is using matrix multiplication will be very natural. Okay, so like this is just identity, then the I actually is a 90-degree rotation. So if we multiply, then it will be equal -1. So this is really the complex number as before. Okay. Then we can write the matrix is something A plus BI. Okay. Yeah. Now there are many famous formula. I think I guess I should to put the complex number using polar coordinate. It will be something like that, and then the multiplication will be something like that. Then the square will be something like that, and then we will have the Mafro formula if n is not just only positive, but even for negative. So by using that one, we can have a formula very easily to expand cosine of 3 theta by to be a single function, so single argument function. So let's, I like to show that how to use the complex numbers for using in SA circuit. Yeah. Let the current SA circuit is the amplitude multiplied by cosine omega t, something like that. Then using the complex numbers, we can see that's the, yes, if put here omega and this sin omega t, then the original I will be real from the complex numbers. Now, if we have a resistor, then the potential will be R multiplied by I. So the R is the quantity of the resistor. Then in the complex number, we should put some extra I sin omega t, and then we can write it. So this is for real quantity, and this is for complex quantity. Then we'll have in the form something like this. So the original will keep something like this. Now if we have the inductor, if we have inductors, then this is, yeah, we should accept this one, or ask him why the inductor has of this formula. Okay. So the potential will be something like that. In order to write it in the complex, the real number should be cosine. So this is changed to be cosine, and then the original complex numbers will be I plus sine, something like that. The amplitude is just follow. And the original quantity will be something like this. Now the problem is to write this one on I. So if we multiply this one, because you know the I is I0 cosine omega t and something like that, then we change again to be like this, and then the complex form is something like that, then the original quantity will be real of I omega Li. Okay. Now, if we have capacitors, so with similar computation, we have something like this. And now, if we have a series of connections, that the sum of the, if we have a parallel, resistor, inductor, and capacitor, then the potential just sum it. And then we have something like this. And so the formula is exactly the same with real numbers when we have potential and we call resistor in the real numbers, and here it's called just impedance. So surprising things, I think, if we have the parallel, then the formula in the real numbers has the exact form. I like to show one more problems. So if I have one quadrilateral, any quadrilateral, and then make it square here, square here, square here, square here. Something, even if this is changed, the connection between the center of this square and between this square is always perpendicular and the same length. Then using the complex numbers, we can solve this one. So by writing this is 2a, 2b, 2c, and 2d, then one of the condition is because it's closed, then the a plus b plus c plus d should be 0. Now the benefit of the complex numbers, we can rotate the vectors for any degree by using suitable complex numbers. In here, if I like to show, if I have 2a, maybe it's better if I drew here, go to up to c easily. Then I should move here in the middle, and then the vector should be rotated by 90 degrees. So in the complex number, just multiply by I. Then the center of the square will be something like this, and because the 0, then the second one should be adding 2a first, go to here, and then now directly to go here. So, because we like to show that the complex number representing the center of the square are the difference between the numbers, and we got this one. And we want to show that if A perpendicular to B, it means that we should show this one or this one. But then by computing this one will be 0, then we have shown that the connecting center of between two center is perpendicular. Yeah, thank you. I think I'm done. So, yeah.
Thank you.
Yeah. Okay.
Thank you for the insightful speech.
Pardon me? Conclusion? Yeah, I mean, if we like to work even for the R, in R, we work to area more bigger, but then we can come back to the goal of this one. Maybe like, for example, like before the square root of -1, and then can be explaining again in R. Right?
Okay. Is there any suggestion, comment, or?
Huh?
Oh, yeah. Okay. Somebody, please. Oh, sorry.
Wono, thank you for your interesting lecture. With
Thank you very much.
Interesting with I, of course. A small remark. You started with the book of Cardano, but actually Cardano did not invent that formula. It was Tartaglia who invented that, and Cardano took it up in his book without his permission, actually.
Okay.
So if you look at the history, it's a very interesting history. With lots of fights and
Okay. Yeah. I don't want to. We should thanks to Cardano because he wrote the books, and then we can see the solution.
He published a book and got the revenues from that book, whereas Tartaglia actually discovered the formulas.
Yeah, I know it. Yeah. Thank you.
Thank you, Dr. Van Horsen. Another one?
Thank you. Professors, I work a lot with MATLAB and in my research, and in MATLAB I use lots of matrices and also the iterations, looping. And in one case, if I just use the default, which is the result will be either real and complex number, the elapsed time or the running programs are very, very high. So if I choose to just use the real type of a number, and it's slowing down the elapsed time of the programs. And also the result is just like a slightly different. And so I come to my conclusion that if I use a complex number in my programs, the elapsed time will be higher. And as the result is not so different, I just use the real type of number because it seems that the complex number slowing down make it higher. And if I just use the real number, my programs goes slower, the time elapsed. So when your slides, one of the titles said that doing it complex number, in my case, I think I don't need that. Is it wise or not to have some conclusion like that?
What I said is not apply for any general situation. Yes, sometimes we need it, sometimes maybe we don't, right? So actually for the MATLAB, I don't know. Maybe as the experts in MATLAB. Okay.
Okay, thank you for the question. But apparently, MATLAB software is also a complicated one, so we cannot answer that question yet. Any other comment or question? No? There is none? Okay, thank you for the insightful lecture, Professor Wono. Give an applause.
Okay, thank you very much to our moderator Trudy Ada Pihandoko MSI for driving the warm discussion between the honorable speaker and all participants.
The Professor Marcus Wono, Setya Budhi, and Rudy Adha Prihandoko MSc, please stay. I would like to call upon Associate Professor Shelton Pairis as the steering committee of the 8th SEAMS-UGM 2019 to come to the stage and pass on the souvenir and the certificate to our honorable speaker and the moderator.